Welcome to the Problems Channel Season 2, Episode 28, the episode which I titled, Is it a hexagon or is it a triangle? Because in this episode we will solve a problem that seemingly deals with a regular hexagon, but upon a closer inspection it turns out that a more straightforward solution of the problem can be generated if we look at a regular hexagon as an equilateral triangle. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the home page of this channel and in the channel's trailer section, find the episode titled The Problems Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E28, we're given a regular hexagon shown over here, and for now, for an interesting and substantial meaty case, we are told that initially we exclude the boundary of that regular hexagon and only consider strictly its interior. In this interior, at random, a point P shown over here, I didn't name it, but it doesn't matter. A point shown over here in red is chosen in the interior of this regular hexagon, and then that point is connected with all the vertices, with all 6 vertices of the regular hexagon. And the question that we are suggested to answer in this problem is the following. Let's say we walk around that point and around the hexagon, let's say counterclockwise, and we pick one triangle, we name it yellow, and then we name every other triangle yellow as well until we come back to the original triangle. And we do the same thing with the remaining triangles. We paint them, let's say, in blue. So now we tile or we partition the interior of this regular hexagon tight without gaps and overlaps with these triangles, and the question is the following. The total area of all the yellow triangles as measured against the total area of the blue triangles. What is the relationship between these total areas? Are they equal, or one of them is larger than the other, and why? And we want to know what is the story behind that question, why the answer to that problem is what it is. And initially, like I said before, we will only consider the case when the point P shown over here, chosen at random in the interior of a regular hexagon, sits strictly inside the regular hexagon. But later on, when we will be discussing a deeper solution of this problem, we will also see what will happen if the randomly chosen point roams the boundary of the given regular hexagon. In the mathematical problem S2E28, we are asked to say something interesting and meaningful about the areas of all the yellow and of all the blue triangles. And we know that the area of every non-degenerate Euclidean planar triangle can be computed in a number of distinct ways. For example, one way to compute the area of a non-degenerate planar Euclidean triangle is to take the half product of the length of 2 sides and the sine of the included angle. But in this problem, we're told that the point P, shown over here in red, is chosen in the interior of a given regular hexagon, is taken at random. That means that the lengths of the sides under consideration and consequently the included angle between them will have no rhyme or reason to them. They will be completely random. So it seems that we lack certain amount information and probably certain good amount information to give an answer to that problem with absolute certainty. We also know that the area of a non-degenerate planar Euclidean triangle can be computed using, for example, the Heron's formula that deals with the perimeter of the given triangle and the length of its sides. And in this problem, we see that just about the only thing that's common to all these triangles is the length of the proverbial base of every such triangle, because the length of that base is specifically the length of the side of a regular hexagon, and the lengths of all the sides are evidently one and the same. So again, the lengths of the sides of the interior triangle shown over here, the yellow and the blue ones, will be also varying in some unknown to us ways. And in the problem statement, we're not given any specific information about the specific location of the point P, other than it is chosen at random and it sits inside a regular hexagon. We can also go back to our favorite proverbial middle school half product of the base and the height of a triangle. We already realized that the length of the base of each triangle is one and the same. So this is one commonality across all yellow and across all blue triangles. However, the heights of these triangles seem to have no rhyme or reason to it. So on the one hand, we think that maybe the person who put this problem together forgot to give us some meaningful information. On the other hand, if we're given this problem with the statement that was given to us, it seems that the person who knows that the problem can be solved with just that amount of information is confident that it can be done. Consequently, based on that reasoning, we now develop a hunch that the answer to the problem may very well not depend on the specific location of the point P chosen at random in the interior of a given regular hexagon. And if that is the case, and if our hunch is correct, then what is the next logical step to carry out? Well, then, if our hunch is correct, the next logical step to carry out is to come up with a configuration of the geometric objects at hand in which the computation can be carried out straightforwardly on the one hand and with absolute certainty on the other hand. And what is such configuration? Well, such a configuration could be when the point P that was chosen at random, shown in red over here in this diagram, sits precisely in the center, let's say circumcenter or in center of the regular hexagon at hand. And in this case, what other idea comes to mind? In this case, the other idea comes to mind is the very symmetry of the main character of this problem, a regular hexagon. Observe that from the standpoint of physics, we have a situation in this mathematical problem that is quite similar. In other words, let us assume for a moment that in a certain physical system, the law of conservation of energy or linear and angular momentum applies. Then if we know the amount of energy in such a system in a state 1, which is, let's say, straightforward to comprehend, and that physical system undergoes a certain transformation and moves from state 1 to state 2, then according to the law of conservation of energy, for example, that system, even in the state 2, will possess the same amount of energy. That energy may change in this way or that way, but because essentially and fundamentally the amount of energy in that system will be one and the same, we sometimes are able to make certain practically advantageous conclusions. The same thing unfolds, or very similar thing unfolds in this problem. If we place our randomly chosen point P precisely in the center of our regular hexagon, for example, in centers, circumcenter, and so on, then it is evident that what? It is evident that due precisely to the symmetry of the parent shape, due to the symmetry of a regular hexagon, the sum of areas of all the blue triangles, for example, this one, and this one, will be what? Will be exactly the same as the sum of the areas of the yellow triangles, this one, and this one. And again, if our hunch and our working hypothesis holds, that means that if we move our randomly chosen point in some way and displace it from its center, position it anywhere inside the regular hexagon, then exactly the same situation will hold. The sum of areas of all the blue triangles will be precisely equal to the sum of areas of all the yellow triangles. And now we need to make our hunch not a hunch, but a solid mathematical fact, and we need to generate at least one convincing proof. And how can we do that? Well, let us go back for a moment to the symmetry of the given geometric shape, a regular hexagon. If you do not know anything about the theory of groups, for example, then do not worry about it. But I just want to say that in real time, again, different people think in different ways. But one way to think about the situation is the following. The reason I bring in the theory of groups into our discussions is because the theory of groups gives us a very meaningful and a very tangible measure or metric of symmetry. And that metric of symmetry could be in general, the cardinality of the group of rigid symmetries of, for example, two geometric shapes, or when the groups are finite, it could be basically the size or the number of elements in such a group. Well, the group of rotational symmetries of a regular hexagon, or the group of all rotations of a regular hexagon in the parent plane about its center by pi over 6 radians, for example, for the sake of being consistent counterclockwise on the composition, is isomorphic to the finite cyclic group C6, because it has 6 elements in it. 6 rotations bring this regular hexagon into coincidence with itself. And the group of all rigid symmetries, rotations in the parent plane about the center, and reflections in its axis of symmetry, will be isomorphic to the finite dihedral group. I'll write it down over here, D2 times 6, which is D12. It's a group that has 12 elements. And precisely because that group of all rigid symmetries of a regular hexagon has 12 elements in it, we can say what? We can say that a regular hexagon is actually more symmetric than a regular pentagon. And the group of all rigid symmetries of a regular pentagon, let me try to portray it halfway decent over here, will be isomorphic to the finite dihedral group D2 times 5, D10, and it will contain precisely 10 elements. 10 is less than 12, hence, from the group theoretic perspective, a regular hexagon is more symmetric than a regular pentagon. Now, the group of all rigid symmetries of a square will be isomorphic, and that group will contain what? Rotations of the square in the parent plane about its center, plus the reflection in its axis of symmetry. That group will be isomorphic to the finite dihedral group D2 times 4, which is D8, and that group will contain 8 elements. And the group of all rigid symmetries, rotations, and reflections of an equilateral triangle will be isomorphic to the finite dihedral group D4, 2 times 3, D6. It will contain 6 elements. Consequently, we can say that a regular hexagon is more symmetric than a regular pentagon. It's more symmetric than a regular fourgon or a square, and it's more symmetric than a regular threegon or an equilateral triangle. But look at this. The number of elements in the group of all rigid symmetries of an equilateral triangle is twice as much. So it has 6 elements, and in this group we have 12 elements. Precisely twice as many symmetries are contained in the group of all rigid symmetries of a regular hexagon than in the group of all rigid symmetries of an equilateral triangle. So now we think, maybe a regular hexagon enjoys a special relationship with an equilateral triangle. And again, this is yet another valid group theoretic move. which amounts to generating a regular hexagon using what? Using precisely an equilateral triangle. How can we do that? Well, let's say we are given two types of triangles. In this case, let's say yellow triangles and blue triangles. Here we have an even number of sides, of course, in the regular hexagon. So we partition all the sides of this regular hexagon into, again, yellow, blue, yellow, blue, yellow, blue. Let's say we take an equilateral triangle that has yellow side over here as its base. What can we do in order to generate a regular hexagon with this equilateral triangle? Well, we can flip it with respect to this side reflected. More specifically, this will be the reflection of the plane in this side over here, this way. I do not want to put too many symbols over here on the board because it will get very busy very quickly, but you understand what's going on. We take an equilateral triangle and reflect the plane with respect to this side, let's say. This is one reflection. And what do we have? We'll have these two triangles. Then we take this triangle and reflect it in this side. And then in this side, in this side, and in this side. So we do 5 consecutive reflections plus the original one, and voila, we have a regular hexagon. But we can do exactly the same thing with, let's say, a triangle that has a blue side over here. So we can take this equilateral triangle, reflect it in this side into this triangle, and then repeat the experiment again. Carry out 5 consecutive reflections, and voila, we generate a regular hexagon. And here you may be wondering, why did Roman give us this problem when we are studying, let me erase this, group theoretic material here. So you guys may be wondering, why did Roman give us this problem, and why does he think that expand and conquer or scope expansion problem solving approach has anything to do with it? Well, I already noted several times in my previous episodes, and I will mention this several more times because this is an ongoing theme in mathematics, theoretical physics, and computer science, is that when we take on any problem in mathematics, even theoretical physics or computer science, willingly or unwillingly, consciously or unconsciously, we still somehow get zoomed in into local material, and that local material becomes the box, and somehow, again, willingly or unwillingly, consciously or unconsciously, we get shackled into that box. And sometimes a fair amount of problems arise precisely because we cannot unshackle ourselves from that box and think out of the box. So in this case, our regular hexagon becomes the proverbial box, and a lot of students will just stay within this box and will not be able to move in anywhere. But again, on this channel, we like to learn how to think out of the box, and the current problem solving approach that we're studying right now is precisely that: scope expansion, or expand and conquer. In addition to its tactical wisdom, that problem solving approach is there to remind us, or be as a constant reminder, that whenever we take any problem, we should always try at least to step out of the box and try to see if the seemingly current whole or large whole can become a smaller part of another whole. And in that expansion of the local material, we should try to find a certain tactical advantage. So what is this scope expansion or expand and conquer driven maneuver that we can execute in this case? Well, the moment we said the words equilateral triangle, symmetry, dihedral, this and that, blah, 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 and we already went through the exercise of reflecting our equilateral triangle in certain sides consistently. We carry out the same operation consistently. What transformation, let's say, what maneuver can we do over here? Well, let's do this. Let me grab yellow, let me grab blue. Let us do this. Instead of reflecting our yellow-based triangle with respect to this side and flipping it over that way so that we form a regular hexagon. Let's see what happens if we reflect that triangle in this yellow base this way. In other words, we reflect it this way. What will happen? Well, what will happen is this. Let me try to draw it this way, and this way. That's one maneuver. And what is the next maneuver? Does anything ring a bell so far? No? Okay. We skip the triangle with the blue base and we reflect the equilateral triangle shown over here that has the yellow base also with respect to the yellow base this way. What will happen? Well, we will obtain this and this. You see? Hopefully by now things begin to look more and more clear. Right? We reflect this way. We skip again the triangle with the blue base, and what do? We take our third yellow triangle, let's say, and reflect it in the yellow base this way, outside. So we go this way. Reflect this triangle with respect to its yellow base. What will happen? Well, we'll obtain this triangle over here. And now what do we have? As if by magic, we have a larger, you see, this is precisely what happens. We obtain a larger geometric shape, an equilateral triangle. Why is this an equilateral triangle? Well, it's easy to prove that the resultant shape will be an equilateral triangle because what? This side is equal to this side in length, of course. I mean, the length of this yellow base is equal to the length of this line segment, this, all these unit, let's say, lengths are one and the same. The final formation is a larger, or let's say a parent triangle, equilateral triangle. This is where the title of this episode is coming from. Now, is that it? Or we can do something else? Well, the answer is we can do something else. We can repeat exactly the same experiment, but this time we will carry out this experiment with respect to what? With respect to our proverbial blue triangles. Exactly. We can reflect, for example, this triangle with respect to its blue base over here. And what will we have? We will have this triangle right here. Flip this guy. In loose terms or officially and pedantically, we carry out the reflection of the Euclidean plane and so on. We do the same thing with this triangle. And what do we have? We have this triangle over here, like so. And if we reflect this triangle with respect to this blue base, what will we have? We will have this triangle and this triangle. So now we have two equilateral triangles. Let's say the blue equilateral triangle and what? And the yellow equilateral triangle. So the truth be told, now what we thought originally that was the box, a given regular hexagon, it's not really the box, and it's not really in some sense the bigger all-containing whole, but it's a smaller part of a bigger picture. This is where we apply the scope expansion or expand and conquer problem solving approach, and this is precisely how we step out of the box. So what is one way, or what is a way to think about our original regular hexagon? What is it? Well, in this slide, a regular hexagon is actually an intersection of two congruent equilateral triangles that are positioned in a very peculiar way that will be tactically advantageous to us in a few seconds. In other words, our regular hexagon is an intersection of two congruent, larger, evidently, equilateral triangles that are positioned in such a way that they share their, let's say, circumcenter or incenter, if you will. And what kind of conclusion can we draw from that? Well, we will make this conclusion in the next segment. Now that we made a crucial scope expansion problem solving approach driven observation in the previous segment that a given regular hexagon is actually an intersection of two congruent equilateral triangles, we can finish the solution of this problem in a quite crisp and elegant synthetic geometry way as follows. We go back to our given regular hexagon, randomly chosen point in the interior of this regular hexagon. We represent or we embed this regular hexagon into two appropriately positioned equilateral triangles, which we explained how to construct in the previous segment. And we ask the following question. Very well, if we were to sum the areas of all the blue triangles, what will we write down for this sum? Well, we represent each such triangle as having the base that is represented by the side of the given regular hexagon. For example, this blue triangle has this side of a regular hexagon as its base. This blue triangle has this side of a regular hexagon as its base, and this blue triangle has this side of a regular hexagon as its base. And just for definitiveness, let's agree that the length of each side of this regular hexagon is L, 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 and so on. So for the sum total of the areas of all blue triangles, what can we write? Well, let's say we use white chalk. It will be half product of the corresponding base, L over 2, times what the corresponding heights. So just for demonstration purposes, I will write H sub 1 and superscript B for the height of the blue triangle 1, H2B for the height of the blue triangle 2, and H2B for the height of the blue triangle number 3. So here we will have H1B plus H2B plus H3B. That much should be understood. This is a little bit of a tricky notation. The letter B is not actually the power, it's just a superscript that designates the color of the triangle, which height is entered over here. H1B is the height of the blue triangle number 1, H2B is the height of the blue triangle number 2, and H3B is the height of the blue triangle number 3. Likewise, when we compute the total sum of the areas of all the yellow triangles, what will we say? Well, for the sum of all the yellow triangles, we will have a similar expression. This time, again, we represent each triangle as having the base as the corresponding side of a given regular hexagon. This base for this yellow triangle, this base for this yellow triangle, and this base for this yellow triangle. And again, the same thing applies to the heights. H1y is the height of the first yellow triangle, H2y is the height of the second yellow triangle, H3y is the height of the third yellow triangle. So here we will have which formula? L over 2, and what will we have in parentheses? In parentheses, we will have the sum of three heights. H1y plus H2y plus H3y. And not that we really need it, but throwing a little bit of geometry into the mix, what can we say? Well, the diametrically opposite sides of each and every regular hexagon are what? They are parallel. For example, this side of our regular hexagon is parallel to this side. Consequently, the perpendicular constructed to this side through this point will also be perpendicular to this side through this point. So instead of seemingly 6 different line segments, we will actually have 3 line segments over here, and in each of these 3 line segments that will be perpendicular to the corresponding pairs of the sides of our regular hexagon. Each such line segment will be partitioned into 2, the height of the yellow triangle and the height of the corresponding blue triangle, and so on. But we do not really need that much, because what do we see now? The multiplicative number, the multiplicative constant that sits in front of both parentheses is what? L over 2. L is one and the same constant, 2 is one and the same constant, the ratio of two constants is a constant. So the answer to the question that was posed in the mathematical problem S2M30 about the magnitude of the total sum of areas of all the blue and all the yellow triangles comes down to what? The answer to that question comes down to what is the relationship between the total sum of heights of our blue and yellow triangles, and what is another way to interpret these heights. Well, each point that represents, for example, let's say this point over here, and where is this point over here for yellow triangles, and for the blue triangles, this point, and this point, they represent what? They represent the respective orthogonal projection of the randomly chosen point onto the corresponding side of each triangle. And through these orthogonal projections, what do we construct, or what do we obtain? Well, through these orthogonal projections, we obtain precisely the distance from the given point to the given straight line. For example, this one, or this one, on this one, on this one, on this one. Consequently, the answer to the mathematical problem S2M30 hinges on the following observation. What can be said about the sum of distances from a point in the interior of the parent equilateral triangle to the sides of that triangle? Why is that? Well, when we construct or compute the total sum of areas of all the blue triangles, let's think carefully. What do? Well, we embed our regular hexagon into the corresponding, let's be careful, yellow equilateral triangle shown over here, because we extend, in some sense, the sides of these blue triangles this way and that way, for example. And then these heights of these blue triangles represent what? This sum over here represents the sum of distances from the randomly chosen point P to the sides of the yellow equilateral triangle. Likewise, when we compute the total sum of areas of all the yellow triangles, what do? Technically, we embed our regular hexagon into where? Into the blue equilateral triangle that is congruent, or that is essentially the same to the yellow equilateral triangle. And then the sum of heights shown over here represents what? Represents the sum of distances from the randomly chosen point in the interior of a blue triangle to the sides of that triangle. And what can be said about the sum of these distances for any equilateral triangle? Well, that much we can figure out fairly expediently. Let's say we have our equilateral triangle shown over here with the side length A, not to get confused and back down with the symbols shown over here on the right. And boom, we throw a random point into the interior of the triangle, and we want to make a certain statement about the sum of distances from this point to each side of that equilateral triangle. What can we say? Well, in this case, we can, let me use white chalk, connect that point with all three vertices of the parent equilateral triangle, like so, you see. And let's say we use, I'll use three different colors over here to do what? What observations can we, what tactical useful observation can we make so that we can extract actionable mathematics from it? Well, that maneuver of connecting the randomly chosen point in the interior of an equilateral triangle with the remaining vertices of that triangle does what? It partitions or tiles the area of the parent equilateral triangle without gaps and overlaps tight. And for example, that such a triangle will be this one. Let's call it a green triangle. This triangle, let's say this will be our yellow triangle, another one shown over here, this triangle, like so. And our favorite blue triangle, let's say this one, this triangle right here. So we argue that in sum, the area of this green, yellow, and blue triangles is equal to the sum of the, to the area of the parent triangle. What is the area of the parent equilateral triangle? Well, let's say, let me use red, let's say this will be the height let me show you this one. That will be the height of our equilateral triangle. Then the area of that equilateral triangle will be what? It will be a half product of A, H, and H on the one hand. On the other hand, each triangle, smaller triangle that tiles our parent triangle's tight, parent triangle tight, can be represented what? As having the base, that is the side of this triangle, and having the height, which is precisely the distance from the point P to that side. So this will be height 1. This distance or this height will be height 2, H2, and this height over here, or that distance, the distance from this point to that side of the parent equilateral triangle, will be H3. And then what can we say about the sum total of the areas of the smaller triangles? Well, it will be the same base, A over 2 times what? Well, times the sum, H1 plus H2 plus H3. In other words, when we cancel A over 2 on one side, A over 2 on the other, what we will have? We'll say that H, or the height of an equilateral triangle, for example, constructed from this vertex, it doesn't really matter in these triangles, is equal to what? Is equal to the sum of distances from our randomly chosen point inside of the triangle to the sides of that triangle, and that is the result. That is the result. That is the key to solving this problem. All the heights in an arbitrary non-degenerate plane Euclidean triangle, that is not the case, but in every non-degenerate Euclidean equilateral triangle, that is the case. The length of the height of such triangle constructed from any vertex is one and the same. The height of this triangle constructed from this vertex, H, is the same as the height of this triangle constructed from this vertex, H, and exactly the same as the height of this triangle constructed from this vertex, H. That means that the sum of distances from the interior point in an equilateral triangle to the sides of that triangle does not depend on the specific position of that point inside that triangle. Now, how do we exercise that observation? Well, we take it and we carry it back into our problem. That sum shown over here of distances from the randomly chosen point to the sides of what? The blue triangle will be equal to the height, let me write it down over here, will be equal to the height of the parent triangle this way. Let's see, let me show you this way, for example, right? It will be H. And the sum of heights shown over here for our blue triangles will be also what? It will be equal to the sum of distances of our randomly chosen point to the sides of the yellow triangle shown over here. But these triangles are what? They're equilateral and they're congruent. And in all congruent equilateral triangles, the length of the heights of these triangles is one and the same. And that fact precisely shows that the areas, the sum total of the areas of the blue triangles will be what? Will be precisely equal to the sum total of the areas of the yellow triangles. And again, we obtain that answer mostly courtesy of the scope expansion or expand and conquer problem solving approach by realizing that in this specific case, it is tactically more advantageous to look at a given regular hexagon not as the box as a given regular hexagon, but as in some fairly loose but fairly accurate, under a fairly loose and fairly accurate artistic license, as an equilateral triangle, as shown in the title of this episode. And more technically, it turned out that it is more advantageous to look at a given regular hexagon as the intersection of actually two congruent equilateral triangles. Now, is that it for this specific problem? It turns out there is actually not it. Much more interesting and beautiful grown up mathematics is associated with that problem, and I will discuss this mathematics in the next segment. I do not mean to sound like an overzealous helicoptering parent who is telling their children what to do all the time, but back in season 1, episode 2, where we explained a way to practice mathematics correctly, we mentioned that every time we solve a given mathematical problem, we should really go through a certain list of things to do. And one of these things to do is to generalize and abstract our solution, or at least try to generalize and abstract a solution of the problem that we just generated. When we abstract a solution of a problem, that means that we are trying to basically come up with a small number of small and simple key ideas that allow us to generate that solution. And when we try to generalize that problem, then we're trying to increase the radius of application of these technical ideas. In this specific case, in the problem S2M30, we dealt with a pronounced two-space case or two-space situation. It turns out that the generalization of this problem can be carried in two directions. We can drill down in the two-space situation, and we also can export this two-space case into the three-space case. Staying within two-space situation, we can say that, for example, of course, in this problem, we basically showed that the total sum of areas of yellow triangles is equal to the total sum of areas of the blue triangles. And in order to do that, we had to partition the areas of these, we have to partition these triangles into two mutually exclusive colors, yellow, for example, and blue. But what does that mean? That means that in general, if we try to expand the radius of application of this idea, then we will need precisely a polygon that has an even number of vertices, or basically 2n vertices. And it turns out that our observation, or the theorem that we proved in this episode, actually holds for any polygon that has precisely 2n or an even number of vertices. For example, it holds for a square, it holds for a regular hexagon, it holds for a regular octagon, and so on. And in this case, it is interesting to see if we can keep going with our synthetic geometry proof that we used during this episode when we proved the statement about the regular hexagon. That's one thing. The other thing is we showed that the sum of distances from a randomly chosen point inside of a regular trigon or inside of an equilateral triangle is independent of the position of that point. Turns out the radius of this idea also can be expanded, and that statement will hold for all other regular polygons, not necessarily the polygons that have an even number of vertices. That's another thing. And there is a way to go into a similar direction, but from a different perspective. For example, let's say we take our regular polygon, any which one, it doesn't matter, even the polygon with an even number of vertices or a polygon with an odd number of vertices, and through the center, this is the key point with this idea, through the center of this regular polygon, we construct a straight line named lambda, and I showed that the center of this regular polygon sits precisely on that line. Then we roll through all the vertices of this regular polygon, compute the distances from these vertices to that straight line. For example, here, distance 1, distance 2, distance 3, distance 4, all the way. Then we square all these bad puppies, and then we sum them. And it turns out that the sum of squares of distances from the vertices of a regular polygon to that straight line that passes through its center is also a constant, which means that in our problem S2M30, the point P can legally roam the innards of a regular hexagon any which way, and this relationship will hold for that anyway. But in the straight line case, it means that if we take any substantial, meaty, interesting, non-trivial transformation, for example, rotate our straight line about the center in the parent plane, come up with the different straight line that passes through the center, construct the distances, square them, sum them, we'll get the same number, which is the same for that particular regular polygon, which means that the sum of distances, the sum of squares of distances from the vertices of this regular polygon to that straight line does not depend on the specific position of that straight line. That position can be anything we want. Now, back in season 1, when we studied the mechanics of the transform and conquer problem solving approach, we solved a number of wonderful problems that dealt with solids. We looked at the ideas of a net of a solid and duals of solids. And we can export the idea that we saw in this problem in 2-space case into the 3-space case as follows. Let's say we take our favorite regular octahedron, position, let's say, this way. Then again, randomly throw a point in the innards of a regular octahedron. And then what do? In the 2-space case, we connected our random point with the vertices of the underlying regular polygon. Here we do the same. Here we take that point and we connect it with all the vertices. Let's say, for example, this vertex and this vertex and this vertex, just to start things off. What the question is, what kind of solid will we obtain when we do that? Well, the answer to that question is straightforward. When we connected our random point with the vertices of a regular hexahedron, we had the side of that regular hexahedron play the role of the base of the underlying triangle. Here we will get a solid called a tetrahedron, and the base of that tetrahedron will be precisely the face. It will be precisely, for example, in this view, it will be this face of a regular octahedron because the point P sits inside our octahedron. We connect that point with this vertex, and this vertex of a regular octahedron. How many planes do we generate that way? Well, we generate precisely 4 planes. One plane is the face of our regular octahedron, that's the base, and 1, 2, and 3 more planes when we connect this point P with these 3 vertices. Question, how many octahedrons like this will we generate? Well, if we connect this point with the remaining vertices, we will generate, let's say, roughly speaking, in the upper portion 4 tetrahedrons, and roughly speaking in the bottom portion another 4 tetrahedrons. In total there will be 8 tetrahedrons, and the statement in this situation that is similar to the problem, to the statement that we made in the problem S2M30 is the following. Let's say we color these smaller tetrahedrons with alternative colors, yellow, blue, yellow, blue, yellow, blue, and so on. And then it turns out that the sum total of all the volumes of the yellow tetrahedrons will be precisely equal to the sum total of the volumes of all the blue tetrahedrons. And the interesting question is, how do we prove that statement? Can it be done using the synthetic geometry or the ideas that come from synthetic geometry in a way that we generated a proof in our problem S2M30? Well, maybe we know that, for example, an regular octahedron and the cube are the duals of each other, which means that a regular octahedron can actually be inscribed in a specific way into a cube, and thus maybe, again, we're thinking the box, the proverbial box that the regular octahedron is not really the box. We step out of that box, think out of the box. Maybe we can somehow construct other volumes built around that octahedron that will be straightforward to deal with. But the answer to that question is the following. Even for our original problem S2M30 and more problems like it, including the problems that deal with 3-space, there exists a straightforward to understand machinery from grown-up mathematics that allows for a straightforward generation of proofs. And this machinery deals with so-called affine functions in, let's say, 2 and 3 variables. The notion of affine functions in mathematics is a sizable chunk of material, and obviously I cannot cover everything that needs to be covered in connection with affine functions in one or even several episodes. But this will be the material that I hope will whet the appetite of curious travelers as an extra for experts. As such, in grown-up mathematics, the function in two variables, let's say f, x, y, let's say these are real numbers, is called linear if it has the following shape: a times x plus b times y. So far so good. So this is the function f, two variables x and y. All numbers here are real, and a and b are constant real numbers. Now, once intuitively speaking we shift or parallel translate all that mess without changing its shape, in other words, if we add constant c, then technically what we'll have is precisely an affine function in two variables, x and y. And for example, it's easy to understand that the affine function in three variables will be what? A times x plus b times y plus c times z plus d, and so on. 4, 5, 6, 7, 17 variables, and so on. Now, the interesting thing with these affine functions is the following. First of all, it is again straightforward exercise to show that the sum and the difference of affine functions will be yet another affine function again. And if we multiply this affine function by a constant real number, what will we obtain? An affine function again. So this will be another constant, another constant, another constant, game over. Template of the affine function in two variables. Geometrically, as an equation, for example, let's say all these things equal to z. What does this affine function in two variables represent? Geometrically, an affine function in two variables shown over here represents a plane in the, let's say, x, y, let's say this will be x, this way runs the y-axis, this is O, this is Z. So in general, geometrically, an affine function in two variables represents a plane that is not parallel to the z-axis, that the plane that runs in some interesting way that is not, let's say, vertical. Now, the interesting question here is this: how can we make sure that our affine function in two variables is uniquely defined? What does it mean? Well, it means that if we have a function, how can we distinguish it from another affine function in two variables that is genuinely distinct and different from this one? Well, should be fairly straightforward to understand that in order to completely define an affine function in two variables, we need what? We need three numbers, three real numbers, a, b, and c. And how can we obtain these numbers? Well, if we have, now we listen carefully, three distinct not collinear points, so that means that what? We will, for example, write z1 equals to a times x1 plus b y1 plus c. We'll have three equations like it, and once we know the value of such a function at three distinct not collinear points, then boom, we lock in the values of a, b, and c, the constants a, b, and c, and that means that we completely define an affine function. And how can we now bring it home as it relates to our problem? In which way? Well, if the given affine function in two variables is constant everywhere, what does it mean? That means that the constants a and b are 0, and that means that geometrically our affine function is represented by a plane that is right now in our designations over here is parallel to the XOY plane, or in some sense a plane that is perpendicular to the z axis. How does all this affine functions in two variables pertain to our situation? Well, the way they pertain to our situation is as follows. In some future episode, we will share with you guys a very elegant and beautiful proof of the following idea. Let's say, let me use some color, maybe blue and some yellow. Let's say we're given a straight line. We'll give a straight line, let's say again, lambda. We'll show it in green. We'll take the point P over here, the point P with the coordinates, let's say x, y. All these events transpire in the Euclidean plane. And now the question is, from the analytical geometry standpoint, how can we compute or express the distance, this distance right here, this distance from a given point to a given straight line in the plane using the material that has nothing but the P and the equation of the straight line lambda. Well, that distance, let's say we call it rho, from the point P to the straight line lambda. Again, it can be shown, it's not too difficult, and in the near future we will show it, can be, this distance is given by the following formula. Let's say we have a straight line lambda that looks like this from the analytical geometry standpoint. A times x plus b times y plus c. This is, let's say, an equation of a straight line in the fixed plane, in a certain plane. Lambda is a times x plus b times y plus c. A, b, c are constant real numbers. Well, then this distance over here from the point P to the straight line lambda is given by what? A times x plus b times y plus c over square root of a squared plus b squared. As a slightly more high wire act in analytic geometry, it can be shown that this equation can be multiplied by certain numbers so that the sum of these squares is 1, so we don't have to write it. But fundamentally, this is the formula for the distance in the plane from a given point to a given straight line that has this equation. Everything is wonderful. What can you say about this formula? Well, exactly. This is our favorite affine function in two variables. How can we see that? Well, we can rewrite it in exactly this way. For example, it could be written like this: a over square root of a squared plus b squared times x plus b over square root of a squared plus b squared times y plus c over square root of a squared plus b squared. And what do we have? Constant variable, constant variable, constant. This is specific. This is a perfect template for our affine function in two variables. And what do we do now? Now I will erase all this material, guys. You keep track of it in your paperwork, but the idea is the following. We will take in the next segment, in this short few minutes, we will show that if we pick the center of our proverbial XY coordinate system to be the center of our regular hexagon, then the point P chosen at random will be precisely this point with certain coordinates x and y, whatever, and each side can be represented by corresponding straight line lambda. All the time the point P is located on the same side of all the straight lines, because the point P is located where? Is located inside of a regular hexagon. This point is on the same side of this straight line, on the same side of this straight line, and so on. And by applying this idea to this configuration, we will precisely prove the statement of the problem S2M30. As we promised in the previous segment, we now take our regular hexagon, locate its center, and into that center we place the origin of a traditional orthogonal coordinate system xy shown over here. In that coordinate system, our randomly chosen point P will have, let's say, coordinates x0 and y0. That point P roams the innards of our regular hexagon, and with respect to all the sides of that hexagon, that point is always located on the same side. For example, if we agree that we walk around the boundary of that hexagon counterclockwise, our left hand always sticks into the regular hexagon, our right hand always sticks outside of it. So if we walk that way, the point P will be on the left side of each and every side of our regular hexagon. Moreover, each and every side of our hexagon will be represented by a corresponding straight line that has a certain equation in that plane. That equation shown over here. Uppercase A, B, C are constant real numbers. X, Y are the coordinates in the chosen plane. This side will have its own equation. This side will have its own equation. This side, and so on. Each side will have its own equation. Will be certain set of real numbers A, B, and C. The point P has coordinates x0, y0, and as we showed in the previous segment, the distance from the point P to the straight line, let's say lambda, which represents each side of our regular hexagon, will be this one, and the distance shown over here, that distance perfectly represents the affine function in two variables. And how does this affine function in two variables is connected to our areas? Well, in our areas, we represent the area of every smaller triangle, yellow or blue, as a half product of the base times the height. The height is the distance, exactly this distance, from the point P to the side of a regular hexagon. The length of the side is fixed. Consequently, the only material that can vary in this case is what? Is precisely this distance. Consequently, each and every area of each and every smaller triangle is, technically speaking, an affine function. And for the yellow triangles, we will have how many, if we sum the areas of all these yellow triangles, how many affine functions in two variables we will have? Exactly 3. And if we sum the areas of all the blue triangles, how many affine functions we will have for the blue triangles? Also 3. So what do we do? Well, now we do a popular maneuver that is carried out in different areas of mathematics. For example, in real analysis, we do it all the time. We construct the difference between the sum total of the areas of all the yellow triangles and the sum total of all the areas of the blue triangles. And we now say what? That difference right here will be what? Will correspond to what? How many? 6 will correspond to 6 affine functions. And we already remember from the previous segment, if the value of our affine function in two variables is one and the same in 3 distinct non-collinear points, then what does that mean? That means that this function is constant. The real numbers a and b are 0. It's constant. It means that that affine function takes on one and the same value everywhere in the plane. And how does that observation apply to us? Well, now that we constructed the difference between the sum total of all the areas of the yellow triangles and the sum total of all the areas of all the blue triangles, then that difference will be represented as 6 affine functions. But what we have on our side is advantageous points that we talked about earlier. Let's say our point P is placed in the center as shown in this diagram over here. What can we say about this difference then? Well, that difference amounts to a big fat 0, because evidently all the smaller equilateral triangles have the same area, and we have an even number of those partitioned in half. 3 blue, 3 yellow. The difference is 0. Wonderful. So now apparently our set of 6 affine functions is 0 at one point. But how many more points we have at our disposal? Exactly, we have 6 points more at our disposal that are quite advantageous. And what are these 6 points? These 6 points are the vertices of our regular hexagon. This guy, this guy, this vertex, this vertex, this vertex, and this vertex. So if we now allow our point P to roam the plane x or y plane, in such a way that it can sit in the vertices of our regular hexagon, then what will happen? Well, let's analyze one case. Let's say we pick the point P to be here. Then we will have how many triangles? Well, one yellow and one blue triangle will be degenerate, but in non-degenerate cases, we'll have two yellow and two blue ones. And what can we say about the difference between the sum total of areas of the blue triangles and the sum total area of the yellow triangles? Again, it will be 0 because this yellow triangle is essentially the same as this blue triangle, and this blue triangle is essentially the same as this yellow triangle. This difference for this, in this case, for the areas will also be 0, and it will be the case for all the remaining 6 points. If we analyze all these 6 points, the case will be the same. So at 7 distinct, not collinear points, our difference, which is 6 affine functions in two variables, is one big fat 0. And what does that mean? It means that that affine function, which is represented as 6, let's say, smaller affine functions, is constant everywhere in the plane. So that means that no matter what position this point P takes, that function over here, that difference will be 0 anywhere in the legal location for the point P in the plane. And that precisely means that the relation shown over here holds. In other words, the sum of areas of all the yellow triangles is equal to the sum of areas of all the blue triangles. Game over, all courtesy of affine functions in two variables. Now, going back to our three-space case, you already understand that the volume of a tetrahedron is what? 1/3 height times the area of the base. The area of the base is one and the same. The only thing that will vary is the height. You have an affine function in three variables and so on, and you know how to proceed further. And now you are armed with the grown-up machinery that is straightforward to understand, and that also allows, in some sense, beautiful and elegant way to generate the proofs for this type of problems. Meanwhile, we will move on to a new challenge next. In our next challenge, the mathematical problem S2E28, we are looking for a mechanical way for constructing arbitrary magic squares of odd order. So the key requirement over here is that the order of a magic square must be odd. As a reminder, a magic square is basically an n by n square table that is filled with numbers in such a way that these numbers sum to one and the same number along the columns, along all columns, along all the rows, and along the two diagonals of the square. And by definition, the order of a magic square is basically the size of its side. And again, just to make sure that we're all on the same page and you do not waste your time trying to do something that may be impossible, the order of magic squares that we're looking to construct in this problem must be odd. Good luck. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present a solution of the mathematical problem S2E28.